So let's just write out the days of the week. You have Monday, day, and we'll call today day one. Day one is a Monday. What I want to figure out is what is day 300 going to be? Day 300. What day of the week will day 300 be? And I encourage you to pause this video and think about that a little bit. So let's just write out the days of the week. You have Monday, use a different color. You have Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, and Sunday. So if we had a lower number here, we could just fill this out. Monday is day 1, Tuesday is day 2, Wednesday day 3, 4, 5, 6, 7. I'll keep going. Day 8, well, that's going to be a Monday again. 9, 10. I'm almost writing a calendar out. 11, 12, 13, 14, 15, 16. So this is kind of useful. I could just write it out if I wanted to figure out something, day 16 or day 20. I could just write that out. But this isn't that helpful if I wanted to figure out day 300, or especially wouldn't be helpful if I wanted to figure out day 3000. So can I come up with some mathematical way of thinking about what day 300 is going to be? Well, as you see, when I started drawing this grid here, this grid has rows, and in each row you have 7 days in it. And that makes sense. There's 7 days of the week. So is there a way that if someone just gave you 16 without drawing this grid, that you would know that 16 is a Tuesday? Well, one way to think about it that might jump out at you is you could divide 16 by 7. That will tell you how many of these rows will come before 16. That will tell you how many rows come before 16. So 16 divided by 7 is 2. You have 2 rows before 16 right over here. You could get 7 into 16 2 times, and then you have a remainder. And then you have a remainder. What is the remainder when you divide 16 by 7? 16 divided by 7, well, is going to be 2. 2 times 7 is 14. You're going to have a remainder of 2. So when we divide, we've historically cared more about this 2. We normally care more about, well, how many times does it go into it? But now the remainder is actually interesting. The remainder is really interesting here. Because the remainder tells you, the first 2 just tells you, well, 7 goes into 16 2 times. That's how many rows you have before getting to the 16. But then the remainder tells you, well, in that row, where is the 16? So the 16 is remainder 2. So the 16 is not the first. It's the second entry in the third row. And so it's going to be a Tuesday. Tuesday is the second day. I know what you're saying. Does that always work? Well, let's try it out with some other examples. Let's imagine day 25. Day 25. So let's just divide 25 by 7. So I'll do it right over. I could do it. Let me make sure I have enough space. So if I have 7 goes into 25, it goes 3 times. 3 times 7 is 21. You have a remainder of 4. So let's see. So based on that, so let me rewrite this. So 25 divided by 7 is equal to 3, remainder 4. So it's equal to 3, remainder 4. So based on this, if we were to write out the grid, we should have 3 rows of 7 before we get to the 25, and then 25 should sit in the fourth column. So if it's sitting in the fourth column, it should be a Thursday. So day 25, based on this little math we just did, should be a Thursday. Let's see if that actually works out. So let's go to 17, 18, 19, 20, 21, 22, 23, 24, and 25. It is indeed a Thursday, but it makes complete sense. You could get 7 rows in it before the row that gets to 25, and then in that row, it's going to be the fourth entry because you have a remainder of 4. 1, 2, 3, 4. It's going to be a Thursday. So now we're ready to answer the question. What is day 300 going to be? So let's just divide 300. Let's just divide 300 by 7 and see where we get. 7 goes into 30 4 times. 4 times 7 is 20. 28. Subtract, you get 2. Bring down a 0. 7 goes into 20 2 times. 2 times 7 is 14. And then we get our remainder. And now we care much more about the remainder. 20 minus 14 is 6. So our remainder is 6. So if we think about what day of the week it is, in its row, it's going to be the 6th entry. It's going to be the 6th column. There's going to be 42 rows above it, but we care about which entry it is in its row. So day 300 is going to be the 6th day of the week, the way we've written it out. It is going to be a Saturday. So let's say I have tables where I can fit one person at either of the short ends of the table. So I could fit one person there, I could fit one person there. You could view this as we're looking from above the table here. So we could put one person at either of the short ends of the table. And then on these longer ends right over here, we can fit two people. We can fit two people at the longer end. So when you have one table, you could fit 1, 2, 3, 4, 5, 6 people. You could fit 6 people. Now let's think about what happens as we add tables end to end to this table right over here. So let's imagine now 2 tables. So here we have one table, and it's going to touch ends with this table right over here. And because it touches ends right over here, we're kind of making it one big continuous table. You can't fit someone here anymore. So now how many people can we fit? see, we can fit 1, 2, 3, 4, 5. And then on this table, which is identical, you could fit 6, 7, 8, 9. And then you could put one person at the end right over here. So when you have two tables, you can now fit end to end, you can now fit a total of 10 people. Let's keep going and see if we can think of a pattern here. So let's put 3 tables here. So 1 table, 2 tables, and 3 tables. So just as before, we could put 1 at each end, so that's 2 people. Then we have 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 folks. 14 folks. So what does it look like is happening here? Well, if you just look at the numbers, we went from 6 to 10 to 14. It looks like we're adding 4 people every time we actually add a table. Now, does that actually make sense? So let's think about this first situation. Let's imagine these are real people, and I'll make this person in blue right over here. If you were to bring over this new table, if you bring over table 2, so this is table 1, if you bring over table 2, this blue person has to move. And so where could they move? Let's say that they always insist on sitting at the end of a table, so the blue person moves to the new end of the table. The new end of the table. They move right over here. So how many new people could move to this combined table now that you brought the second table in? Well, the new people I will do in this purple color. The new people are that person. Let me do it in a more unique color. This person, this person, this person, and this person. So you were able to add 4 new people with a new table. One way to think about it is a new table is going to have one usable end here. That usable end is going to be taken by the person who was already at the usable end of when you had less tables. And so you're really able to, the real addition is the 2 sides here. So you're adding 4 people every time you add a table. So it makes complete sense. So based on this, you could think about, without even having to draw these diagrams, what would happen or how many people you would be able to fit if you had 4 or 5 or 6 or however many tables. So you can imagine if you have 4 tables, we just have to add 4 and you should be able to sit 18 people. If you have 5 tables, you should be able to fit 22 people, and on and on and on. I want to make little townhouse shapes with toothpicks. So this would be my first townhouse. I've used 3 toothpicks so far, 4, 5, and 6. So that is my first townhouse. And let me make a little table here keeping track of things. So I'll do that in white. So here's my table to keep track of things. So this is a number of houses, and then this is the toothpicks that I'm using to make that house. So this first toothpick, or the first house here, took me 6 toothpicks. 1, 2, 3, 4, 5, 6. Now let's make our second house. And these are going to be townhouses. They're going to share common walls. So I'm going to add 1, 2, 3, 4, 5 toothpicks for my second house. Now, why did I only have to add 5 and not 6? Well, they shared a common wall here, so I didn't have to add another toothpick here for this left-hand side wall. So starting with the first house, I really just had to add 5 toothpicks. I had to add 5 toothpicks to get to now 11 total toothpicks if I want 2 houses. I think you see the trend here. What about 3? What about 3 of these? Well, this is going to be another 5. 1, 2, 3, 4, 5 toothpicks. So we're going to add 5 again. We're going to add 5 again and get to 16. Let's do 4 just for good measure. So the fourth one, we're going to add another 5. 1, 2, 3, 4, 5. So the fourth one, we're going to add another 5. Gets us to 21. Now, I want to think about, can we, using this pattern, figure out how many toothpicks it would take for us to, say, make 50 of these townhouses, or even 500 of these townhouses, or even 5,000 of them. And we just have to look at this pattern here and see, can we come up with an equation for each of these actual values? So for example, we see a pattern that, well, we already recognize that we started with 6 and we're adding 5 every time we add a house. So when you add the second house, you add 5 once. The third house, you start with 6 and you add 5 twice. The fourth house, you start with 6 and you add 5 3 times. So let's actually write that down. So 21 is equal to, you start with 6, you start with this 6 here, You start with 6, and then you add 5 3 times. Plus 5 times 3. When you had the 3 houses, once again, you started with 6, and you added 5 2 times. You added 5, we do that same color. And you added 5 2 times. Plus 5 times 2. When you had 2 houses, you started with 6 again. This is equal to 6. And you added 5 once. So plus 5 times 1. And then when you had one house, when you had one house, and it'll fit the same pattern, you started with 6. And how many times did you add 5? Well, you didn't add 5. You could say that you added 5. You added 5 0 times. So you might see a little pattern here. However many houses you needed, you take one less than that, multiply it by 5, add that to 6, and you get the number of toothpicks. And actually, let me rewrite this. So I could rewrite this as 6 plus 5 times 4 minus 1. I could write this as 6 plus 5 times 3 minus 1. You could write this as 6 plus 5 times 2 minus 1. You could rewrite this as 6 plus 5 times 1 minus 1. And maybe that makes the pattern a little bit closer or clearer. This 4 is right over here. This 3 is right over here. This 2 is right over here. And then this 1 is right over here. So now I think we are ready to think about what would happen if we wanted to make 50 houses. So let's try to do that. So this right over here is, I'm going to do that in orange. This right over here is our 50th house. So this is the shared left wall it has. This is the 50th house right over here. So how many total toothpicks for 50 houses? So if we have 50 houses, well, we can use the pattern that we came up with. It's going to be equal to, starting with our 6, the first house requires 6, and then we're going to add 5 for each incremental house. So plus 5 for each incremental house. And how many incremental houses are there going to be? Well, they're going to be 50 minus 1 incremental houses. Why minus 1? Well, you already built one of them with the 6. Then for every extra one, so there's going to be 49 extra houses, you're going to add 5 toothpicks apiece. So this is going to be equal to 6 plus 5 times 49. And that is 245. So 6 plus 245 is equal to 251 sticks. And what's really neat about this pattern we just came up with is you could use it to figure out how many sticks you would need for 1,000,000 of these little toothpick townhouses. Alan found 4 marbles to add to his 5 marbles currently in his pocket. He then had a competition with his friends and tripled his marbles. Write a numerical expression to model the situation without performing any operations. So let's think about what's going on. So he already had 5 marbles in his pocket. So he already had 5 marbles in his pocket. And then he found 4 more marbles to add to that. So we can add the 4 marbles to the 5 marbles. So 4 marbles plus the 5 marbles. So that's what happens after the first sentence. He found 4 marbles to add to his 5 marbles currently in his pocket. He then had a competition with his friends and tripled his marbles. So this is how many marbles he had before tripling, and now he's tripling. Now he's tripling his marbles. So we'd want to multiply 3 times the total number of marbles he has now, times 4 plus 5. So this right over here is the numerical expression that models the situation without performing any operations. We of course could then actually calculate this. He has 9 marbles before tripling, and then you multiply it by 3, and he has 27. But this is what they're asking for. They want us to write this expression. What I want to do is think about whether this expression right over here would evaluate the same way whether or not we had parentheses. So to think about that, let's first think about how it would evaluate if we have the parentheses. So if we have the parentheses, we want to do whatever in the parentheses first. And so here we have 8 minus 3, which is equal to 5. So this simplifies to 5 times 8 minus 3. And now we want to do the multiplication before we do subtraction. This goes back to order of operations. You do your multiplication and division first. Well, you do your parentheses first. Then, if you have multiplication, division, addition, and subtraction all in a row, you want to do your multiplication and your division first. So here we're going to multiply 5 times 8 to get 40. And then we're going to subtract 3 to get 37. Now let's think about what this would evaluate to if we did not have the parentheses. So it would be 8 minus 3 times 8 minus 3. So we just have to remind ourselves about the order of operations. The convention is to do your multiplication first. So you're actually going to multiply the 3 times the 8 before you subtract it from this 8 and then before you subtract this 3. So we took away the parentheses, but the order of operations say, hey, do this multiplication first. We could even put a parenthesis here to emphasize that. So this will become 8 minus 24. So let me write it this way. 8 minus 24 minus 3. 8 minus 24 minus 3. Now 8 minus 24 is negative 16. You subtract another 3, you're going to get to negative 19. So clearly you get very, very different values depending on whether or not you have parentheses. What I hope to do in this video is give ourselves some practice interpreting statements and writing them as mathematical expressions, possibly using parentheses. So let's get started. And for any of these statements, if you get so inspired, and I encourage you to get so inspired, pause the video and see if you can write them as mathematical expressions. So this first one says 700 minus 19 divided in half. So we could say, another way to think about divided in half is divided by 2. So we could write this as 709 minus 19, and we're going to do that first, so that's why I put the parentheses around it, divided by 2, or divided in half. That's one way that we could write this. Now the next one, and once again, pause it if you get inspired, and I encourage you to. 3 times the sum of 56 and 7. So it's going to be 3 times the sum of 56 and 7. So the sum of 56 and 7, we want to take that first. So it's going to be 56 plus 7. That's the sum of 56 and 7. And then we want to do 3 times that. We want to do 3 times this sum. So we could write it like that. Another way we could write it, when you're dealing with parentheses, and you're going to see this more and more as you get into more and more fancy algebra, I guess you could say, but what I'm about to show you isn't so fancy, is you don't have to write the multiplication sign here. You could just write 3 and then open parentheses, 56 plus 7, 56 plus 7, and this too is 3 times the sum of 56 and 7. And you want to be very careful, because you might be tempted to maybe do it without the parentheses, so you might be tempted to do something like this, 3 times 56 plus 7. But this one isn't obviously 3 times the sum of 56 and 7. In fact, the standard way to interpret this is that you would do the multiplication first. You would do 3 times 56 and then add 7, which is going to give you a different value, and you can try it out than if you were to add the 56 and the 7 first. So to make sure that you do the 56 and the 7 first, you want to put this parentheses around it. So let's keep going. The sum of 3 times 56 and 7. So we're going to take the sum of 2 things. So we're going to take the sum of 2 things. The first thing that we're going to take the sum of is 3 times 56. So 3 times 56 and 7. And let me do it in a different color. And 7. And 7. So this right over here is the sum of 3 times 56 and 7. Now it's always good to write the parentheses. It makes it a little bit cleaner, a little bit more obvious. Look, I'm going to take the 3 times 56. I'm going to do that first, and then I'm going to add 7. But based on what I just told you, the standard way, if someone were to just write 3 times 56 plus 7, plus, let me write it, 3 times 56. If someone were to just write this, 3 times 56 plus 7, this actually can still be interpreted as the sum of 3 times 56 and 7. Because as I just said, the standard, the convention, so to speak, is to do your multiplication first. Order of operations, which you may or may not, but if you're not familiar, you will be familiar with it soon, is to do the multiplication first and then add the 7, or then do the addition. But just to make it clear, it doesn't hurt to put the parentheses there, 3 times 56 plus 7. Now we have 43 minus the sum of 16 and 11. So 43 minus, so we're going to have 43 minus the sum of 16 and 11. So minus the sum of 16 and 11. So from 43, we're going to take the sum of 16 and so 4. 4 times as large as the expression 175 minus 58. So I'm going to do 4 times as large as something, so I'm going to multiply something times 4. And I'm going to multiply 4 times as large as the expression 175 minus 58. 175 minus 58. And once again, I could write it as 4 times as large as the expression, let me do that in that purple color, as the expression 175 minus 58. Either way. And once again, if you were to do it like this, if you didn't write the parentheses, then it wouldn't be the same thing. Because if the parentheses weren't here, then you would want to do the 4 times 175 first and then subtract the 58, which isn't what the statement is telling us. And this last one, I think, brings up an interesting thing for us to think about. Because if someone were to walk up to you on the street and they were to show you, whoops, what's going on with my computer? And they were to show you 2 different expressions. And well, the first expression said 2, let's write 7 and figure out what that's going to be. That's hard. That's going to take, not hard, it's out. Well, I'll read this. Well, the first expression said 2, let's write it this way. Actually, I'm not going to speak them out. I'm going to write it down. I'm just going to write some crazy number here. Some crazy numbers here. So that's one expression that someone were to write. And let's say another one is this one. And I'm intentionally, I put the commas in the wrong place. Let me make sure I get this right. All right, that's 183,576. This is 37,399. So that's one expression. And then another expression is this. And I'm intentionally not reading it out. Well, I'll read it out a little bit. 37,399. If someone said, quick, which expression is larger? And you might be tempted, or you might not be tempted, but you might be tempted, oh, let me calculate this thing. Gee, I'm going to have to write this thing down or use a calculator or something or whatever else to add 183,576 plus 37,399. And then I'm going to have to multiply that by 2 and figure out what that number is equal to. And then I would have to take 183,576. The following table contains the first 5 terms of given pattern A. Generate pattern B according to this rule. For every term of pattern A, so they give us the terms of pattern A here, multiply the term by 3 and add 1 to get the corresponding term of pattern B. Then graph the pairs of corresponding terms. So for every term in pattern A, we want to multiply by 3 and add 1. So if we multiply 0 by 3, we get 0, and you add 1, you get 1. You multiply 1 by 3, you add 1. So if we multiply 0 by 3, we get 0, and you add 1, you get 1. You multiply 1 by 3, you get 3, and then you add 1, you get 4. 2 times 3 is 6, plus 1 is 7. 3 times 3 is 9, plus 1 is 10. Remember, we're just multiplying by 3 and adding 1. 4 times 3 is 12, plus 1 is 13. So those are the corresponding terms for pattern B. And then they ask us to graph them. So let's try to graph these points. So when pattern A is 0, pattern B is 1. When pattern A is 0, so this is pattern A equaling 0, that's our horizontal axis, the value of pattern A. Pattern B is the value of our vertical axis. Pattern B is 1. When pattern A is 1, pattern B is 4. So it's 1, 4. So when pattern A is 1, pattern B is 4. Pattern B is on the vertical axis. When pattern A is 2, pattern B is 7. So 2 and 7. When pattern A is 3, pattern B is 10. So 3, 10. So 3 in the horizontal direction, that's our pattern A value, and our pattern B value is 10. And then finally, when pattern A is 4, pattern B is 13. Pattern B is 13. Now let's just look at these patterns. We see pattern A is increasing by 1 each time, while pattern B is increasing by, pattern A starts at 0 and increases by 1, while pattern B starts at 1 and increases by 3, which makes complete sense. It makes sense it starts at 1 because all of these you multiply by 3 and add 1. So you start at 1, and then the fact that we're multiplying by 3, that's what's leading to the distance between these points being 3. So let's check our answer, make sure we got this right, and we did. The following graph represents the first 5 terms of 2 given patterns. In the answer box, there are different statements about the 2 patterns. Choose all correct statements. So here for each point, this point right over here, this represents its horizontal coordinate is the first term of pattern A, which is 4, and its vertical coordinate is the first term in pattern B, which is 1. And then we can do that for the other points as well. So actually, let's figure out what the values are. So we have pattern A, and then we have pattern B. So the first term for pattern A is 4, and when pattern A is 4, the first term for pattern B is 1. The second term for pattern A is 7. And when pattern A is 7, pattern B is also 7. Third term, pattern A is 10, and pattern B is 13. And then fourth term, pattern A is 13, and pattern B is 19. And then finally, fifth term, pattern A is 16, and pattern B is 25. Now before even looking at these, let's see what we can think about these patterns here. So it looks like pattern A starts at 4, and it increases by 3 every time. To go from one term to the next, you just have to add 3. Now what about for pattern B? Well, pattern B starts at 1, and every term here, it looks like you're adding 6. When pattern A increases by 3, and we're moving in the horizontal direction, based on the fact that pattern A is represented on the horizontal axis, we're going to move up 6 in the vertical axis, and we see that here. Pattern A increases by 3. Pattern A increases by 3 from one term to the next, and when that increased by 3, pattern B increased by 6 from one term to the next. Pattern B increased by 6 from one term to the next, and we see that it keeps doing that. Now let's think about what we have over here to see which of these statements actually apply to this. For every term in pattern A, multiply the term by 2 and then subtract 7 to get the corresponding term from pattern B. So let's see if that holds up. So according to this, if this was true, I should be able to take this, multiply by 2, and subtract 7 and get that. So let's see, is 1 equal to 2 times 8 minus 7? Or sorry, 2 times 4 minus 7. So 2 times this number, 2 times 4 minus 7. Well, 8 minus 7 is equal to 1. Is this right over here equal to 2 times this 7 minus 7? Well, yeah, it's equal to 7. Is 13 equal to 2 times 10? 2 times 10 minus 7. Yeah, 20 minus 7 is 13. Is 19 equal to 2 times 13 minus 7? 26 minus 7 is 19. Is 25 equal to 2 times 16 minus 7? Well, 32 minus 7 is 25. So this first statement checks out. For the corresponding term, the value of pattern B is 2 times the value of pattern A minus 7. Now let's look at the second one. The terms of pattern B are always greater than or equal to their corresponding terms from pattern A. Well, no, that's not right. It's true for a couple of scenarios. Here, for the third, fourth, and fifth term, actually for the second, third, fourth, and fifth terms, pattern B is equal to or greater than pattern A. But for the first term, it's not true. Pattern A is greater. So this is not right. To get from each point to the next, you need to move 3 units to the right and 6 units up. Well, that's exactly what we talked about. From one term to the next, pattern A, along our horizontal axis, we increase by 3, while pattern B, we increase, which is plotted on our vertical axis, by 6. So you move 3 to the right and 6 up. So that is right. The second terms of both patterns are 7. Well, yeah, we see that right over here. The second terms are 7. We have 7 here, and we have 7 there. And so that is right as well. So the only one that doesn't apply is this second one. This is not right. Below are ordered pairs that represent the first 6 terms of 2 given patterns. The first value in each pair is a term from pattern A, and the second value is a term from pattern B. In the answer box, there are different statements about the 2 patterns. Choose all correct statements. So let's think about what's going on here. They said the first term is pattern A. So pattern A, so the first term in each of these coordinates is pattern A, or in each pair is pattern A. So pattern A goes from 1 to 2 to 4 to 8 to 16 to 32. So it looks like pattern A, to go from the first term to the second term, we multiplied by 2. We multiplied by 2, and then go from the second to the third term, we also multiplied by 2, and we just keep multiplying by 2. Multiply by 2, and we just keep doing that. 8 times 2 is 16, 16 times 2 is 32. Now let's think about what's going on with pattern B. Pattern B. So pattern B is the second number in each of these pairs, and it's just always 3. So there's a couple of ways to think about it. You could just say pattern B is always 3. You could say pattern B starts at 3, and we're just adding 0 every time. Or you could say that pattern B starts at 3 and we are multiplying by 1 every time. Either of those would give you just 3 showing up over and over again. Over and over again. So now that we've looked at these pairs, which show the corresponding terms for pattern A and pattern B, let's look at the choices here and see which of these apply. In pattern A, you can get from any term to the next by multiplying by a constant number. Well, that looks right. We go from the first term to the second term by multiplying by 2. Then we multiply by 2 again to get to the third term. Then we keep multiplying by 2. So that constant number that we're multiplying by to get to the next term is 2. So this looks right. The next pair should be 52, 3. So let's think about this. If we keep doubling for pattern A, so it's going to be times 2. 32 times 2 is 64. And then if we say that this is 1 times the previous term, we're just going to get a 3 again. So it should be 64, 3 should be the next one. They say the next pair should be 52, 3. So that's not right. If we graph the pairs, the points will be on the same line. So let's think about that a little bit. Let's think about that. So this is my vertical axis. This is my horizontal axis. On the horizontal axis, I will graph pattern A. And on my vertical axis, I will graph pattern B. Pattern B. And let's see, pattern A goes all the way up to 32. So I'm going to try my best here. So let's say that this is 32, then half of that is going to be 16, half of that is going to be 8, half of that is going to be 4, half of that is going to be 2, and half of that is going to be 1. So these are all the points on pattern A, but for any of them, the corresponding term on pattern B is 3. So we have when pattern A is 1, pattern B is 3. 1, 3. When pattern A is 2, pattern B is 3. When pattern A is 4, pattern B is 3. When pattern A is 8, pattern B is 3. When pattern A is 16, this is like a tongue. When pattern A is 16, pattern B is 3. When pattern A is 32, pattern B is 3. And you see, they all sit on a line. They all sit on the line. They all sit on this horizontal line, or at least the way that we've drawn it. They all sit on this line that you probably can't see in yellow, so let me do it in this red color. They all sit on this line right over here. So this looks right. If we graph the pairs, the points will be on the same line, so I'll go with that one. In pattern B, you can get from any term to the next by multiplying by a constant number. Well, yeah, even though every term is the same term, but you can get from a 3 to a 3 by always multiplying by 1. 1 is a constant number, so we're just multiplying every term by 1. So that also seems to be right. So all of these are right except the second one. The next pair isn't 52, 3, it's going to be 64, 3. You are given the following starting numbers and rules for 2 sequences of numbers. So the first sequence, sequence X, starting number should be 1, and then the rule is add 1. Sequence Y, starting number should be 5, and then the rule should be add 5. Fill in the table with the first 3 terms of X and Y, then plot the ordered pairs X, Y on the graph below. So let's see, sequence X. They say the starting number should be 1. So the starting number is 1, and then the rule, to get to the next number, you just add 1. So 1 plus 1 is 2. 2 plus 1 is 3. Fairly straightforward. Now let's look at sequence Y. They're saying the starting number should be 5. Starting number 5. And then the rule is to get the next term, we just add 5. So 5 plus 5 is 10. 10 plus 5 is 15. Now they want us to plot these things. So let's see. And we plot them as ordered pairs. So we're going to have the point 1, 5. So when X is 1, Y is 5. We see that there. X is 1, Y is 5. When X is 2, one thing to answer. The terms in sequence Y are blank. We've got some apples here and we've got some oranges. And what I want to think about is what is the ratio? What is the ratio of apples to oranges? To oranges. And to clarify what we're even talking about, a ratio is giving us the relationship between quantities of two different things. So there's a couple of ways that we can specify this. We can literally count the number of apples, 1, 2, 3, 4, 5, 6. So we have 6 apples. And we could say the ratio is going to be 6 to 6 2. And then how many oranges do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9. It is 6 to 9. The ratio of apples to oranges is 6 to 9. And you could use different notation. You could also write it this way. 6 to, you would still read it as the ratio as being 6 to 9. But we don't have to just satisfy us with this, because one way to think about ratios, especially if we're thinking about apples to oranges, is how many apples do we have for a certain number of oranges. And when you think about it that way, we can actually reduce these numbers, as you might have already thought about. Both 6 and 9 are divisible by 3. So just how like we can reduce fractions, we can also reduce ratios. So if you divide 6 and 9 both by 3, 6 divided by 3 is 2. 6 divided by 3 is 2, and 9 divided by 3 is 3. So we could also say that the ratio of apples to oranges is 2 to 3. Or if we want to use this notation, 2 to 3. 2 to 3. Now, does that make sense? Well, look, we divided each of these groups into 3. So one way to think about it, so if you divide this whole total into 3 groups, so one group, two groups, and 3 equal groups, we see that in each of those groups, for every 2 apples, we have 3 oranges. For 2 apples, we have 3 oranges. For 2 apples, we have 3 oranges. So, once again, the ratio of apples to oranges, for every 2 apples, we have 3 oranges. But we could think about things the other way around as well. We could also think about what is the ratio. Ratio of oranges to apples. Oranges to apples. And here we would essentially switch the numbers. The ratio of oranges to apples. Notice, up here we said apples to oranges, which is 6 to 9, or 2 to 3 if we reduce them. And here we're going to say the ratio of oranges to apples. So we swapped these two, and so we're going to swap the numbers. Here we have 9 oranges for every 6 apples. So we could say the ratio is going to be 9 to 6. The ratio is 9 to 6. Or if we want to reduce it, for every 3 oranges, so we're going to divide this by 3. So for every 3 oranges, we are going to have 2 apples. We are going to have 2 apples. So notice, this is just exactly what we had up here, but when we had apples to oranges, it was 6 to 9, 6 apples for every 9 oranges. And now when it's oranges to apples, we say it's 9 to 6, 9 oranges for every 6 apples. Or we could say for every 3 oranges, we have exactly 2 apples. Let's do some example questions dealing with ratios. So we're told the table shows the number of people waiting in line for different rides at an amusement park. So 15 people are waiting in line for the roller coaster, 4 people for the slingshot, 12 people waiting in line for the roundup. This is the roundup right over here, to the number of people waiting in line for the slingshot. So there's 11 people waiting in line for the roundup, and there are 4 people waiting in line for the slingshot. So the ratio is 11 to 4. Or for every 11 people in line for the roundup, there are 4 people waiting in line for the slingshot. Let's do another example. Katie loves to read. In the last few months, she has read 3 graphic novels, 2 mysteries, 4 science fiction novels, and 21 comic books. What is the ratio of sci-fi novels to comic books? So once again, pause this video and try to work it out on your own. All right, so we want to know the ratio of sci-fi novels. So she has 4 sci-fi novels. The ratio of that to comic books. She has 21 comic books. So the ratio is for every 4 sci-fi novels, she has 21 comic books. Let me do that other color. She has 21 comic books. So the ratio is 4 to 21. The ratio of sci-fi novels to comic books. 4 sci-fi novels for every 21 comic books. Let's do one more example. This is bananas to... Let's think about another scenario involving ratios. In this case, let's think about the ratio of the number of apples. To, instead of taking the ratio of the number of apples to the number of oranges, let's take the number of apples to the number of fruit. The number of fruit that we have over here. And I encourage you to pause the video and think about that on your own. Well, how many total apples do we have? We have 2, 4, 6, 8 apples. So we're going to have 8 apples. And then how much total fruit do we have? Well, we have 8 apples and we have 3, 6, 9, 12 oranges. So our total fruit is 8 plus 12. We have 20 pieces of fruit. So this ratio is going to be 8 to 8 to 20. Or if we want to write this in a more reduced form, we can divide both of these by 4. 4 is their greatest common divisor. And so this is the same thing as a ratio. 8 divided by 4 is 2, and 20 divided by 4 is 5. So 2, 2, 5. Now does this make sense? Well, if we divide everything into groups of 4, or if we divide into 4 groups, I should say. So 1 group, 2 groups, 3 groups, and 4 groups. And that's the largest number of groups that we can divide these into so that we don't have to cut up the apples or the oranges. We see that in each group, for every 2 apples, we have 1, 2, 3, 4, 5 pieces of fruit. For every 2 apples, we have 5 pieces of fruit. And this is actually a good opportunity for us to introduce another way of representing ratios, and that's using fraction notation. So we could also represent this ratio as 2 over 5, as the fraction 2 over 5. Whenever we put it in the fraction, it's very important to recognize what this represents. This is telling us the fraction of fruit that are apples. So we could say 2/5 of the fruit, of the number of fruit, I guess I could say, of number of fruit, is equal to the number of apples, right? Let me say 2/5 of fruit, if we're speaking in more typical terms. 2/5 of fruit are apples, are apples. So once again, this is introducing another way of representing ratios. We could say that the ratio of apples to fruit, once again, it could be 2 to 5.
to the actual Algebra course as fast as possible because I have the two other tests to take this summer in like in a timely manner.
Let's say that I'm working in a restaurant and I'm making $10 per hour, but on top of my hourly wage, I also get tips each hour. So this entire expression, you can view this as how much I might make in a given hour. Now, you might also realize that the number of tips or the amount of tips I might make in an hour can change dramatically from hour to hour. It can vary. 1 hour, it might be lunchtime, get a lot of tips, people might get some big ticket items. The next hour, I might not have any customers, and then my tips might be really low. So the tips part right over here, we consider that, the entire word, we consider that to be a variable. From scenario to scenario, it can change. So for example, in one scenario, maybe it's lunchtime, I'm getting really big tips. So tips is equal to, let's say it's equal to $30. And so the total amount I might make in that hour is going to, we can go back to this expression right over here. It's going to be 10 plus, instead of writing tips here, I'll write 30 because that's what my tips are in that hour. And so that is going to be equal to, 40. Let me do that yellow color. It's going to be equal to $40. But let's say right after that, the restaurant slows down, we're out of the lunch hour for whatever reason. Maybe the restaurant next door has a big sale or something. And so the next hour, my tips go down dramatically. My tips go down to $5 for that hour. Now I go back to this expression. The total I make is my hourly wage plus the $5 in tips, plus the $5 in tips, which is equal to $15. As you see, this entire expression, the 10 plus tips, it changed depending on what the value of the variable tips is. Now, you won't see whole words typically used in algebra as variables. We get lazy, and so instead we tend to use just easier to write symbols. And so in this context, instead of writing tips, maybe we could have just written 10 plus t, where t represents the tips that we get in an hour. And so then we would say, okay, what happens when t is equal to 30? Well, if t is equal to 30, then we'd have, let me write, so what happens when t is equal to 30? Well, then we have a situation, t is equal to 30. This evaluates to 10 plus 30, which would be 40. What would happen if t is equal to 5? Well, then this would evaluate to 10 plus 5, which is equal to 15. Now, I want to be clear. We didn't even have to use t. We didn't even really have to use a letter, although in traditional algebra, you almost do use a letter. We could have written it as 10 plus x, where x is your tips per hour. X might not be as natural. It's not the first letter in the word tips. Or you could have even written 10 plus star, where you could say star represents the number of tips in an hour. But it just might have not made as much intuitive sense. But hopefully this gives you a general idea of just what a variable is. All it is a symbol. All it is a symbol that represents a symbol that represents varying values, and that's why we call it a variable. What I want to do in this video is think about how expressions are formed and the words we use to describe the different parts of an expression. And the reason why this is useful is when you hear other people refer to some expression and say, oh, I don't agree with the second term, or the third term has 4 factors, or why is the coefficient on that term 6? You'll know what they're talking about and you can communicate in the same way. So let's think about what those words actually mean. So we have an expression here. The first thing I want to think about are the terms of an expression, or what a term is. And one way to think about it is a term of an expression are the things, or the terms are the things that are getting added and subtracted. So for example, in this expression right over here, you have 3 things that are getting added and subtracted. The first thing, you're taking 2 times 3, you're adding that to 4, and then from that you're subtracting 7y. So in this example, you have three terms. The first term is 2 times 3. The second term is just the number 4, and the third term is the number, or is 7 times y. Now let's think about the term factor. And when people are talking about a factor, especially in terms of an expression, they're talking about the things that are getting multiplied in each term. So for example, if you said, what are the factors of the first term? The first term refers to this one right over here, 2 times 3, and there's 2 factors. There's a 2 and a 3, and they are being multiplied by each other. So here you have 2 factors in the first term. What about the second term? The second term, right over here, this was the first term. The second term here has only 1 factor, just the 4. It's not being multiplied by anything. And the third term here, once again, has 2 factors. It's the product of 7 times y. So we have 2 factors here. We have a 7 and a y. And this constant factor here, this number 7 that is multiplying the variable, also has a special name. It is called the coefficient of this term. Coefficient. And the coefficient is the non-variable that multiplies the rest of the term. That's one way of thinking about it. So here's 7y, even if it was 7xy or 7xyz or 7xyz squared, that non-variable that's multiplying everything else, we would consider to be the coefficient. Now let's do a few more examples. And in each of these, I encourage you actually right now to pause the video. Think about what the terms are. How many terms are there in each? each expression, how many factors in each term, and what are the coefficients. So let's look at this first one. It's clear that we have three things being added together. This is the first term, this is the second term, and this is the third term. So this is the first term, this is the second term, this is the third term. And they each have two factors. This first one has the factors 3 and x. The second one here has the factors x and y. And this third one has the factors y and z. Now, what are the coefficients here? Well, remember, coefficients was a non-variable multiplying a bunch of other variables. And so here, the coefficient in this first term right over here is a 3. Now, you might be saying, well, what about the coefficients on these terms right over here? Depending on how you think about it, one way to say is, well, xy is the same thing as 1 times xy. So some people would say that, hey, you have a coefficient of 1 here on the xy, or it's implicitly there. It wasn't written, but you're multiplying everything by 1. And that might be subject to a little bit of interpretation one way or another. Now, this one is really interesting because if we look at the bigger expression, if we look at the whole thing, it's clearly made up of three terms. The first term is x, y, z. The second term is x plus 1, that thing, whole thing, times y. And then the third term is 4x. And if you look at that level, if you look at the first term and you say, well, how many factors does that have? Well, you would say that it has three factors, x, y, and z. How many factors does the second term have? Well, you could say, well, it has two factors. One factor is x plus y, and then the other factor is y. It's multiplying x plus, or sorry, the first factor is x plus 1, and the second one is y. It's multiplying this expression. This expression itself, the smaller expression itself, is one of the factors, and the other one is y. And then this third one also has two factors, a 4 and an x. And if someone said, hey, what's the coefficient on this term? You say, hey, look, the coefficient is the 4. Now let's look at this one over here. Actually, before I look at that one, what was interesting about this is that here you had a little smaller expression itself acting as one of the factors. So then you can go and then zoom in on this expression right over here, and you can ask the same question. On this smaller expression, how many terms does it have? Well, it has two terms, an x and a 1. Those are the two things being added or subtracted, and each of them have exactly one factor. So when we're giving these, you can keep nesting these expressions to think about when you talk about terms or factors of terms, you have to really specify what part of the nesting you're thinking about. If you're talking about the terms of this whole expression, there's 1, 2, 3. But then if you go, you could look at this sub-expression, which itself is a factor of a term, and say, oh, well, there's only two terms in this one. Now let's look at this one. How many terms? Well, once again, there's clearly three. Actually, let me add one more because I'm tired of expressions with three terms. So I'm just going to add a 1 here. So now we clearly have 4 terms. This is the first term, second term, third term, fourth term. And how many factors are in each of them? Well, this is interesting. You might say, well, the factors are the things that are being multiplied, but here I'm dividing by y. But remember, dividing by y is the same thing as multiplying by its reciprocal. So it would usually be considered to have three factors here, where the factors are 3, x, and 1 over y. If you multiply 3 times x times 1 over y, you're going to get exactly what you have right over here. So you would say this has three factors. If someone asks, what's the coefficient here? Well, you'd say, well, that 3 is the coefficient. Here, how many factors do you have? And this is a little bit tricky because you might say, well, isn't 5x squared times y, isn't that equal to 5 times x times y? And you'd be right, and this would be very tempting to say that you have 4 factors, but the convention, the tradition that most people use, is that they consider the exponent of, with x as a base, as just one factor, as just one factor. So traditionally, people will say this has 3 factors. It has a 5, x squared, and a y. X squared is just considered a factor, and once again, what's the coefficient? It's the 5. So with that in mind, how many factors here? Well, you have 3 factors here. You have an x, you have a y squared, and you have a z to the 5th. And then finally, this last term, it's a constant term. How many factors does it have? Well, it's just 1. It's just got 1 sitting there. It's not being multiplied by anything. We are asked to evaluate the expression 5 to the x power minus 3 to the x power for x equals 2. So pause this video and see if you can figure out what happened. What does this expression equal when x equals 2? All right, now let's work through this together. So what we want to do is everywhere we see an x, we want to replace it with a 2. So this expression for x equals 2 would be 5 to the second power minus 3 to the second power. Well, what's that going to be equal to? Well, 5 to the second power, that's the same thing as 5 times 5. And then from that, we are going to subtract 3 times 3. 3 times 3. And now order of operations would tell us to do the multiplication or do the exponents first, which is this multiplication. But just to make it clear, I'll put some parentheses here. And this is going to be equal to 5 times 5 is 25 minus 9, which is equal to, what's 25 minus 9? It is equal to 16. So that's what that expression equals for x equals 2. Let's do another example. So now we are asked, what is the value of y squared minus x to the fourth when y is equal to 9 and x equals 2? So once again, pause this video and see if you can evaluate that. All right, so here we have variables as the bases as opposed to being the exponents, and we have two different variables. But all we have to do is wherever we see a y, we substitute it with a 9, and wherever we see an x, we substitute it with a 2. So y squared is going to be the same thing as 9 squared minus x, which is 2. That minus looks a little bit funny. Let me see. So this is going to be 9 squared minus x, which is 2 to the fourth power. Now what is this going to be equal to? Well, 9 squared is 9 times 9. So this whole thing is going to be equal to 81. This whole thing right over here is 9 times 9. 9 times 9 is that right over there. And then from that, we're going to subtract 2 to the fourth power. Well, what's 2 to the fourth power? That is 2 times 2 times 2 times 2. So this is going to be 2 times 2 is 4. 4 times 2 is 8. 8 times 2 is 16. So it's 81 minus 16. Now what is that going to be equal to? Let's see, 81 minus 6 is 75, and then minus another 10 is going to be 65. So there you have it. Y squared minus x to the fourth, when y is equal to 9 and x equals 2, is equal to... What I want you to do is evaluate the expression 5x squared when x is equal to 3. Pause this video and have a go at that. All right, well, we just have to think about every place we see an x, we'll now replace it with a 3. So this is going to be equivalent to 5 times, instead of x squared, it's going to be 5 times 3 squared. And we know from order of operations, we do the exponents first. That's why I actually put a parentheses around the times 6 to the x power. And I want to evaluate it is equal to 45. Let's do another example that's a little bit different. Let's say I have the expression 1/3 times 6 to the x power, and I want to evaluate it when x is equal to 2. Pause the video again and see if you can work that out. Well, we'll do the exponent first, order of operations, times, and 1/3 of 36 is equal to 12. And we're done. by y is the same thing as multiplying by its reciprocal. So it would usually be considered. So this whole thing is going, because everywhere we see an x, we want to replace it with a 2. So this expression, we just have to think about every place we see an x, we'll now replace it with a 3. So this is going to be equivalent to 5 times, instead of x squared, it's going to be 5 times 3 squared. And we know from order of operations, we do the exponents first. That's why I actually put parentheses around the times 6 to the x power, and I want to evaluate it, is equal to 45. Let's do another example that's a little bit different. Let's say I have the expression 1/3 times 6 to the x power, and I want to evaluate it when x is equal to 2. Pause the video again and see if you can work that out. Well, we'll do the exponent first, order of operations, times, and 1/3 of 36 is equal to 12. And we're done. 6 to the x power, and I want to evaluate it. Pause the video again and see if you can work that out. Well, we'll do the exponent first, order of operations, times, and 1/3 of 36 is equal to 12. And we're done. 6 to the x power, and I want to evaluate it. To evaluate it,